I'm going to tell you what milestones, baselines, and the design and development lifecycle is all about. Hi, I'm Daryl Frank. I'm a principal systems engineer with over 25 years experience in military aircraft weapon systems integration and certification. I even wrote a book called Requirements to Reality to explain this exact mystery. Let me start with a confession. When you're a new engineer, milestone reviews sound terrifying. SRR, PDR, CDR. They sound like secret military acronyms designed to keep you confused. But here's the truth. Milestones are not about paperwork. They're about confidence. Confidence that we understand the problem, we are designing the right thing, that we've built it correctly, and that we can safely deliver it to someone who'll actually use it. These reviews are event-driven confidence checks, not calendar events where engineers present dreams. And every one of these milestones is linked to something called a baseline. Let's start by defining a baseline. In systems engineering and config management, a baseline is commonly defined as a collection of approved documents that describe the configuration of a system. That definition is consistent with configuration management practice and how technical baselines are managed across the lifecycle. Think of a baseline as a frozen snapshot of agreement with documents and artifacts that describe the terms of the agreement. It's a reference point, or more realistically, this is what we agreed to before somebody thought, hey, wouldn't that be nice to add on? Once something is baselined, changes are allowed, but they are controlled, justified, and tracked. Milestone reviews exist to say, yes, this baseline is where we currently are, and it's mature enough to move forward. Every project starts the same way. Someone says, we need a thing. That thing evolves from vague needs and ideas, into numbers, into designs, into hardware and software, and into something that must actually work. Each milestone locks down one level of understanding and establishes a new baseline. So let's walk through them using a maritime patrol aircraft as an example. Imagine this requirement. We need a maritime search and rescue aircraft to operate along the Antarctic coast from a base at the Prince Edward Islands. It sounds reasonable, but it's also completely unbuildable because there are many unanswered questions. So we need to turn those thoughts into technical requirements. Range, endurance, payload, sensors, crew. The purpose of the system requirements review is to ask, do we understand the problem? At SRR, we're not talking about solutions yet. We are asking, are the requirements complete? Are they consistent? Are they testable? Do they make sense in the real world? And this establishes the requirements baseline. And this also includes the functional baseline, which is a list of what we expect the product to actually do. For our aircraft, this means the required range in nautical miles, the required search and rescue capability, the required sensor performance, the required operating temperatures. SRR is where quiet failure is initiated if the requirements are not carefully researched and analyzed. If your requirements are wrong or poorly defined, everything downstream will be beautifully designed and verified, but may still not fulfill its purpose. Next is the preliminary design review. The purpose of the PDR is to establish, do we have a believable solution? At the PDR, we've moved on from what to how. Requirements have been allocated to systems and subsystems, preliminary architectures are defined, and early design trade-offs are made. This creates the allocated baseline. For the aircraft example, radar requirements are allocated to a specific radar system, endurance requirements are allocated to fuel and engines and aerodynamics, search and rescue requirements are allocated to observation and recovery systems. The crew workload is allocated to avionics and automation. PDR is essentially saying, if we keep going in this direction, the design remains compatible with reality and is buildable. So what happens after PDR? This is the make it real phase. Between PDR and CDR, the critical design review, the project enters what I'd like to call the experimental development phase. This is where optimism meets physics. At PDR we said, yes, This looks like a believable solution. Between PDR and CDR, we now have to answer, can we actually build this? So what actually happens here? First, design maturation. Those nice block diagrams and tidy architecture from PDR, they get turned into detailed designs, real interfaces, real dimensions, real tolerances. Next, prototypes, engineering models, and simulations. This is where engineers, they actually build breadboards, create engineering development units, run software builds, create realistic simulations. Engineers hook things together in temporary ways that work. These are not production items. They are there to find problems early and cheaply and prove that the final design will be feasible. If something is going to fail, this is where you want it to fail. Then comes serious analysis. This is where structural analysis stops being rough and becomes detailed. Thermal models meet worst-case scenarios. Safety analyses start answering uncomfortable questions. Reliability predictions appear with actual numbers. In other words, don't tell me about it, show me the solution. Every requirement must now have a clear design solution, a defined verification method. Anything vague gets clarified. Anything unnecessary quietly disappears. Anything untestable becomes illegal and also must be resolved. By the end of this phase, we are ready for CDR. CDR is the critical design review. The purpose: we show that we're ready to build a potential final product. At CDR, the design is no longer a suggestion. Drawings are mature, interfaces are defined, software architecture is locked. Test specifications are nearing maturity, and the customer has validated the design. Validation is extremely important and refers to the criteria that may be qualitative and may not be captured in the technical requirements. So the overall design is what the customer had in mind. CDR establishes the initial product baseline. For our aircraft example, the radar model is chosen, the structure is fixed, the avionics layout is defined. After CDR, changes get expensive, time-consuming, and emotional, because approved design and development and testing and documentation may have to be redone. This is why CDR is taken very seriously in the product lifecycle. After CDR, something very important happens. The design stops becoming a suggestion. From this point onwards, the question is no longer, is this a good idea? The question becomes, does this actually work? Hardware is built for real. Software is integrated end-to-end. Manufacturing processes are exercised for the first time. Subsystems finally meet each other. Integration, also known as the pain phase, begins. This is where interfaces get tested for real. Timing issues appear. It worked on my bench stops being a valid sentence. In a perfect world, the CDR prototype would be your first production item. You would hope that you could slap a label on it and send it to your customer. And this is where engineers learn that tolerances matter, drawings that were technically correct, but things still don't quite fit, software doesn't quite work as expected, and this is where most engineering schedules slip. But that's why good programs plan for it. This is normal. This is why the phase exists. Verification testing happens during this phase. This is serious, requirement-based testing. Environmental tests, functional tests, performance tests. Every test answers one question. Does the system meet this specific requirement? Evidence is collected, failures are documented, and fixes are controlled. This is not innovation time. This is convergence time. In parallel, manufacturing readiness. While engineers are testing, build instructions are written, quality checks are defined, supply chains are exercised. Repeatability is assessed because MRR is not asking, can we build one? It's asking, can we build this again and again and again? At the SVR or TCR, we review test results, verification evidence, deviations and waivers, and this establishes the verified product baseline. For our theoretical aircraft, the range tests are passed, the sensor performance is verified, the cold weather operation is demonstrated, search and rescue mission profiles are validated, and this review answers one question: does the system meet its requirements? It doesn't say, is it nice, is it pretty, or do we like it? Between CDR and MRR, we prove it works and prove we can keep building it. At the manufacturing readiness review or production readiness review, we prove we can build this repeatedly and safely. This establishes the final production baseline and is often tied to certification. For the aircraft, production processes are proven, quality controls exist, supply chains are stable, and the certification evidence is complete. In other words, we're not just building one, we can build many, and safely to the same standard. And then finally, the FCR or PCA, the final completion review or physical configuration audit. The purpose? Does the delivered system match the paperwork? This is the final sanity check. The physical configuration audit confirms the system was built exactly as documented, all the changes were approved, and the delivered configuration matches the baseline. This establishes the as-built or operational baseline. For our aircraft, the serial aircraft matches the drawings, the software versions are known, the mods are recorded, the documentation reflects reality. This baseline is what operations, maintenance, future upgrades will live with for the life of the product. So in closing, milestones aren't about slowing projects down. They're about preventing expensive surprises. Baselines aren't about paperwork. They're about shared understanding and control. If you remember nothing else, remember this. Every milestone asks one simple question: are we confident enough to move forward? If you enjoyed this breakdown, like, subscribe, and remember, engineering isn't about being clever, it's about being consistently right. Check the description for the link to my book, Requirements to Reality, which explains systems engineering in simple language.